talked about in the last module the solution of Schrodinger wave equation for simple harmonic oscillator. I said you that simple harmonic oscillator solution has two different methods. One is by using the ladder operator, which we talked about in details in the last module, and another is power series method. In power series method, more of mathematics is involved, and those of you from who have not done mathematics at the earlier level may have some problem, but the slides which I will be showing you and I will be giving you will have every step done, and it involves very simple differentiation and then some power series concepts also. So I will talk about in details, and I hope none of you will have any issue, even if you have not done mathematics at your BSc level or prior to this course. If you have done mathematics at the +2 level, that will be enough for doing these courses. But keep it in mind that whatever be the method, whether this ladder operator method or power series method, our goal is the same, that we have to find out the eigenvalue and the eigenfunction of the system in the discussion. And our system is simple harmonic oscillator, for which we have found the eigenvalue and eigenfunctions through through operator method, ladder operator method, and now we are going to do the same with the power series method. In power series method, what is written here is the Schrodinger wave equation: d square psi by dx square plus 8 pi square m by h square e minus v psi, and the potential energy which we have already calculated, which is 1 by 2 k x square. So if you put the potential energy value 1 by 2 k x square, you get this particular equation, E minus 1 by 2 k x square, and this is your Schrodinger wave equation. Now, if you replace this equation with the if you multiply the 8 pi square m by h square multiplied by E and multiplied by 1 by 2 k x square, you get this equation: d square psi by dx square plus 8 pi square m e h square psi minus 4 pi square m k x square divided by h square psi. Okay. So it's simple multiplication. We have removed the bracket and it's simple multiplication. Then we treat these two as a constant: 8 pi square me by h square as alpha and 4 pi square m k h square by beta. And if you use these two constants, then your equation reduces to d square psi by dx square plus alpha psi minus beta square x square psi. Okay. So it's simple. Up to this, there is not much of mathematics. Now we know that omega, which is the angular frequency, is written as 2 pi nu with the linear frequency 2 pi nu, and this is equal to root under k divided by m. So k becomes equal to 4 pi square nu square m, and nu is 1 by 2 root under k divided by m. This I talked about in the previous module in details, that how do we reach at this relationship, nu is equal to 1 by 2 root under k divided by m, where I talked about the classical concepts of simple harmonic oscillator. Now if you use this and if you put the beta value, I try to find out the beta value comes out to be m omega h cross, m omega h cross. So beta is equal to, your beta square is 4 pi square mk divided by h square. So beta is equal to 2 pi h root under mk, and then beta becomes equal to 2 pi divided by h root under 4 pi square nu square m square, and this becomes equal to m omega h. Okay, where, and if you put this, this equation remains same. So these calculations, we are meant to tell you that beta becomes equal to m omega h cross square. So this you have to remember, nothing else. Okay, and this becomes alpha minus beta square x square psi. If now the next step is, we have to find out the solution for this equation, for this equation, and in this equation the variable is x. Now we want to change this variable. The normal way of doing power series method is to change the variable, and we will consider beta is equal to root beta x, y is equal to root beta x, a new variable y is a new variable, and this new variable becomes equal to, we suppose it to be root beta x, and if it is so, then dx we can write as dy divided by root beta, and d square psi by dx square we can write as beta is equal to d square psi by dy square. If you use these two, and how do we reach at these? This I have given you in details. So d square psi by dx square you can write as ddx of d psi by dx, and this you can write as d dx of d psi by dy and dy by dx. So that dy and dy goes and you go back to the previous equation. Okay. Then again this equation we can write as d by dy, d psi by dy, dy by dx, dy by dx. Again you remove these two colored part and then again you go back to the left hand side equation, and so this can be written as d square psi by dy square and dy by dx square, dy by dx whole square. And this d square psi by dy square is what? D square psi by dy square, dy by dx becomes equal to beta and d square psi by dy square. Okay. So since y is equal to root beta x, so dy by dx will be equal to dy by dx whole square will be equal to beta. So this is the explanation for how do we write this one, okay, mathematically. Now if you use these change of variables equation, y is equal to root beta x, then your original equation, which was actually this equation becomes this one, beta d square psi by dy square plus alpha minus beta square x square psi. Okay. So this x square is still there. We will remove this also. We will change this to y and we will see how to change it. Okay. The first thing is, which I have done is that I have used d square psi by dx square. This d square psi by dx square is equal to beta d square psi by dy square. Okay. So this equation and this equation we have used in the previous one. Okay. And we get this equation. If you use this one, then what we can write? You divide it by beta, the whole equation you divide by beta, and you get d square psi by dy square plus alpha divided by beta minus, no, it was earlier beta square, now becomes beta x minus beta x square psi. Okay. So if dividing by beta will give you this one. That's very obvious, but if you want I can write dividing by beta will give you this equation. Okay. Now I suppose y is equal to root beta x, so y square will be beta x square, and now we can write this as beta x square, we can replace beta x square by y square here. Okay. So now the equation which you have does not have any x, it has only y. So change of variable is complete by now. D square psi by dy square becomes plus alpha divided by beta minus y square psi. Okay. So if we go ahead, so this is the equation which we have to solve. This is up to till now it is the Schrodinger wave equation where we have changed the variables and we did nothing, okay, except changing the variables and using some constants alpha and beta. Okay. So we need a solution for this particular equation, which is the double differential equation, and we have done many solutions for double differential equation. But the problem with this equation is that it is very difficult to solve this equation. An asymptotic solution can be obtained for a very large value of y. That is, we can have a solution for this equation only when this y is much larger than alpha divided by beta. For example, I have given you the limiting behavior. A solution is, this is an example, that fx is equal to x square plus 3x. For very large value of x, 3x becomes negligible. For very large value of x, 3x becomes negligible and the function becomes equivalent to x square as x tends to infinity. So this is called asymptotic solutions. So for very large value of solution, very large value of y, alpha divided by beta can be neglected, and then the solution becomes easier, with which you are already aware. Because alpha divided by beta we have neglected. So if you neglecting alpha divided by beta, we get this particular equation, d square psi by dy square minus y square psi. Okay. Now this solution is known to you because we have the solution, we have done the solution in particular in a one dimensional box also, that d square psi by dx square is equal to k square x is equal to psi. Okay. So minus kx square is equal to psi. If you are aware of d square psi by dx square minus kx square k square psi is equal to 0. So this solution we have already done. You have done this solution, k square psi. Okay. because there if you remember, it was, what was the solution? d square psi by dx square plus 8 pi square m by h square e minus v e psi is equal to 0. This was the equation. Okay. So this we suppose that 8 pi square m e by h square, and this was the solution, d square psi by dx square plus k square psi is equal to 0, and for this we found the solution. Okay. So if we have done this one in the similar way, we have we can write the solution for this equation, also double differential equation, in terms of y, and this will be an exponential solution. Psi will be equal to exponential plus minus y square divided by 2. Okay. This solution we can write, and you can check that whether this is a solution or not. So if you write this psi is equal to exponential plus minus y square divided by 2, then you can differentiate once. What you get is y exponential plus minus y square divided by 2, and you again repeat this differentiation. What you get is this one, and this becomes equal to the same equation, d square psi by dy square minus y square psi. Okay. So this becomes equal to, for very large value of y square plus minus 1 could be written as y square, and then you get the same solution back here. Okay. So this tells you that a solution for d square psi by dy square minus y square psi could be obtained by writing the exponential form, and this is what we do. We don't need the solution of equation number 2, we need a solution of equation number 1, but it is an approximation that for very large value of y, alpha divided by beta we have neglected. And so what the solution which you have written here in equation 3 is the solution of equation number 2, not equation number 1. This you remember. Okay, because this way will come back. Okay. Then having said that this is the solution of equation number 3, now we have two different solutions. Exponential plus minus y square divided by 2 could be written as exponential plus minus y square plus y square divided by 2 or minus y square divided by 2. Now if you write exponential plus y square divided by 2, then it is not an acceptable solution, because it becomes infinite, and in an infinite solution is not possible. A wave function must be finite, that we have done. The basic property of well-behaved wave function is that wave function should be finite. So the only acceptable solution out of the two different exponential plus minus y square divided by 2 is negative solution, and this is an acceptable solution. This solution is an acceptable solution. Psi is equal to exponential minus y square divided by 2. Okay. And remember this is the solution of equation number 3, equation number 2, not equation number 1. d square psi by dy square minus y square psi. Okay. Then what does this suggest? That this is the only solution which is possible. Okay, general solution of equation. And if it is a solution of equation number 2, equation number 2, the solution of equation number 2, we have found that the solution is exponential minus y square divided by 2. It means that any solution of the equation number 1 which we actually require must have this term exponential minus y square divided by 2. This is the only conclusion which we can draw. In what form, what will be the solution, that we will see, but we say that the general solution of equation number 1 must contain should have a factor exponential minus y square divided by 2. Okay. And if it has this solution, then what we can do is that we can write a solution for equation number 1 as another factor, added factor is f, and rest of the factor we obtain for exponential minus y square divided by 2. So this is the solution of equation number 1 which we actually require, including f. Now you have to find out what is f. Okay. So the solution for equation number 1 could be written in the form of psi is equal to f exponential minus y square divided by 2. If this is the solution, this could be written, then you write d psi by dy, and what do you get? And then again you write d square psi by dy square. What I have done, I have differentiated it. So the differentiation will have this term, and once we have this term, then we can write d square psi by dy square, and d square psi by dy square comes out to be exponential minus y square divided by 2 d square f y df minus f y df divided by dy minus f y square. Okay. So one differentiation and second differentiation will result into this equation, of equation number 4. Okay. Now, this equation could be rearranged to give you this solution. D square psi by dy square is equal to exponential minus y square divided by 2 d square f dy square minus 2y df dy plus y square minus 1 into f. So, this is your equation number 5. It's simple differentiation, two terms you have, you differentiate one and keep the second constant and you get these two equations. Okay. So, once you get this one, substituting the value of psi from equation 4 and that of d square psi by dy square from equation 5 in equation 1. So, we have an equation for the psi value, we have an equation for d square psi by dy square, and if you use these two equations, equation number 4 and equation number 5, and go back to equation number 1, which was d square psi by dy square alpha divided by, what was the solution? We should go back. Equation number 1 was this d square psi by dy square plus alpha divided by beta minus y square psi. So, the psi value also we have found and d square psi by dy square also we have found in equation number 4 and 5, and we replace these. If you put these values into equation number 1, what you get is this one. Okay. So, this was your d square psi by dy square and this is your psi value. So, just put these values, this is your d square psi by dy square and this is your psi value. So, now if you put these two values, you go to the equation number 1. Okay. Now, if you expand these terms, what do you get? If you multiply it and you see, you take e square minus y square exponential minus y square divided by 2 common, and then you get this one. So, this and this term is same, this term will go, this term will go, okay, and then you have this equation d square f by dy square minus 2y df divided by dy plus alpha divided by beta minus 1 into f exponential minus y square divided by 2. Okay. Having done this, what we get is, since exponential minus y square divided by 2 is not 0, so except at y plus minus 1, the expression within the bracket must be equal to 0. So, if for this equation to be valid, either this should be 0 or this should be 0. Okay. So, we say that this expression is actually equal to 0, and if you equate this, then you get equation number 6. I have numbered it as equation number 6, d square f divided by dy square minus 2y df divided by dy plus alpha divided by beta minus 1 into f. Okay. This equation is known as Hermite differential equation. Now, you see this is a new term, Hermite differential equation. It's a general relationship which is already known in mathematics called Hermite polynomial, and we will see what is Hermite polynomial. The solution of this equation is obtained in a polynomial method. So, this we will come across in many times in quantum mechanics. If we are doing simple harmonic oscillator and we get a Hermite equation and Hermite polynomial. If you go for rigid rotor and you do the theta equation, then you will get Legendre equation and Legendre polynomial. If you go for hydrogen atom and you do radial part of the wave functions, then you get Laguerre equation and Laguerre polynomial. Okay. So, all this you will come across in the future modules I will talk about, but this is the normal power series method, is the method which is used for rigid rotor, also for hydrogen atom also. So, learning this at this stage is very important. If you understand here all the calculations, then it will be easier in the other modules where I will talk about rigid rotors and hydrogen atom. Okay. So, a polynomial method is used for doing this calculations. Okay. And what is the polynomial method? In the polynomial method, what we do is that we write this f function, f, which is the additional term we have written as a power series, and we say that f can be written as a naught plus a1y plus a2y square plus a3y square in a series. You can write it. Okay. And if you write this, then we can differentiate it df divided by dy, and we can also find out d square f by dy a square, and then we can put this equation back into the Hermite equations. Okay, back into this Hermite, because what you need, what you required is, in this Hermite equation you have f, you have df divided by dy, and you have d square f divided by dy square. So this you have to find out, and I said you that this f function can be written in a power series. Okay, so that's why the name, that power series method of solving the Schrodinger equation of simple harmonic oscillator. Okay, and how to do this up from the Hermite equations we will do in the next module. Okay, thank you. So in the previous module I derived the Hermite differential equations, and the Hermite differential equation is d square f by dy square minus 2y df divided by dy plus alpha divided by beta minus 1 into f is equal to 0. We were doing the Schrodinger wave equations for the simple harmonic oscillators, and solving, we are using the method of power series method. And in power series method I said you that how from the very basic equations we can reach up to the Hermite differential equations. For this Hermite differential equation solution, we say that f term could be written as in a power series, in an infinite series, and that infinite series which we can write is like this one: f is equal to a naught plus a1y plus a2y square plus a3y cube plus a4y4. Since in the Hermite differential equation we have f df by dy and d square f by dy square. So for finding out the df by dy and d square f by dy square, we will differentiate, and the differentiation will give you, here a naught term will go because you do not have a y, and a constant differential will be 0. So a1y will become a1, and a2y square will be 2a2y, a3y cube will be 3a3y square, and so on. It's a simple differential equation with which all of you are aware. Okay. Once you do this one, then again the second differentiation we can do, d square f by dy square is equal to 1 into 2 a square a2, and 2 into 3 a3y, and 3 into 4 a4y. So we have f, we have df by dy, we have d square f by dy square, and this will change the Hermite differential equation. And if you put these values into the Hermite differential equation, substituting these equations in equation number 6 will give you this equation, equation number 7. So from here up to this is d square y by dy, d square f by dy square. So look at this equation, I have put these equations, this one minus 2y into df divided by dy, alpha divided by beta minus 1 a naught, alpha divided by beta minus 1 a1y, okay, plus alpha divided by beta minus a2y is y2, and so on. You can write other terms. This is the first term, this second term, this third term, this fourth term, from here f terms. Okay, so at this was your, this part is from here to here, it is df divided by dy. Okay, so this we have, this is already there in the same slide, df divided by dy I have written. The color coding I have done, and what we say with this color coding is that for this equation to be valid, the equation can be satisfied only if the coefficients of each power of y is 0. So the color coding is with the power of the y in the equation. See, if you look at the green colors, 1 into 2 a2, you do not have a y here, so it is y raised to the power 0. Alpha divided by beta minus 1 a naught, you do not have a y here, so it is y raised to the power 0. Okay, so if you separate these equations for each power of the each coefficients of the y, then you can write for y naught you have this equation. For y1 it is this equation, okay, and for y3 it is this, y2 it is this, okay. So in general for yk we can write like this one. Look at this again equation back. So this equation is valid only when each coefficients of each power of y is equal to 0. So this green is for y raised to the power 0. So this is y raised to the power 0. This is y raised to the power 0. Okay. Then this is y raised to the power 1. Okay. See 2ya1, this is also y raised to the power 1. So this is also y raised to the power 1. This is also y raised to the power 1. Okay. Same way you can write higher terms also, and the general terms which I have written here is like this one. It is k plus 1, 3 into 4. So, k plus 1 into k plus 2 is 3 into 4. Then a k plus 2, k is what? 2. So, it is a k plus 2, a4 you have to write. So, 2 plus 2 will be 4, a4, and then alpha divided by beta minus 1, 2 into 2. So, 2k into ak is equal to 0. So, a general term you can write from this one like this one, where k is equal to 2. So, you can write this one, k plus 1 into k plus 2, ak plus 2, alpha divided by beta minus 1 minus 2k is equal to ak in terms of. So, since it's a power series and there are large number of terms, so we need a general solution. We have written the for y is equal to 0, y raised to the power 0, y raised to the power 1, y raised to the power 2. You can write it for y raised to the power 3, y raised to the power 4, or y raised to the power 5. Any equations you can write, and it will be more and more complicated equation. So, in general, the y raised to the power k equation should be like this one. It's a general equation. Okay. When you use this equation and rearrange this one, what you get is a k plus 2 could be written like this one, where k is an integer, k is equal to 2. I have said you looking at the equation for this one, y raised to the power k, y raised to the power 2. If it is y raised to the power 2, then k is equal to 2. If it is y raised to the power 3, then it will be something else. If it is y raised to the power 4, then k will be something else. So, it could be anything. Okay, not always 2. 2 only when we are talking about y raised to the power 2. Okay. So, the rearrangement will give you a k plus 2 minus alpha divided by beta minus 1 minus 2k, and k plus divided by k plus 1 into k plus 2 into ak, where k is an integer. This equation is called recursion formula. This is known as recursion formula. Again, this is a term which we will use time and for again, with which you can generate many different terms. Ak plus 2, put a is equal to 0 and you will k is equal to 0 and you will get a2. Put k is equal to 1, you will get a3. Put a is equal to 2, you will get a4. Put a is equal to k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, and you can differentiate generate different terms. Okay. So, it allows the calculations of a k plus 2 of the term y k plus 2 in terms of the coefficients a k and y k. This is what it tells you, that in terms of a k you can determine the value of a k plus 2. So, if we set a1 is equal to 0 arbitrarily, we can obtain, means a1 is equal to 0 means k is equal to 0 actually. This k is 0. Then you can generate a2, a4, a6 and even sets. Okay. Means from k is equal to 0, you generate a2. From k is equal to, once a2 is generated, you put the 2 value here, you can generate a4. Once a4 is generated, you put 4 here, you will generate 6. So, you get an even series. If you put k is equal to 0, then you generate a3, and if you once a3 is generated, you put 3 value here, you generate a5. Once a5 is generated, you put a5 value here, k is equal to 5, and you generate a7 value. So, putting 0 value gives you an even series, and putting 1 value gives you an odd set of equations or odd set of terms of the you can generate from the recursion formula. Okay. But remember that the series which you have taken is an infinite series. Okay. So, here also a solution of Schrodinger wave equation in terms of this series also will give you infinite number of terms, and the solution will be infinity. So, this is not possible. This cannot be done. Okay. So, what you need to do is that, therefore, in order to restrict the number of terms in the series, a condition is introduced, and the condition is that for certain values of k, say n, the numerator of the above equation 8 becomes equal to 0. So, we say that for certain values of k which is equal to n, at which it has to finish it up, series should end at that k value, the series should end, and for that we say that the numerator becomes equal to 0. Numerator of equation number 8 equals to 0, and in order to just truncate the series, because otherwise the solution will have infinite number of terms which we don't want. Okay. So, if we do this one, means alpha divided by beta minus 1 minus 2k becomes equal to 0. So, alpha divided by beta minus 1 minus 2k equal to 0, and I say at k I have written, you see, value of k say n. So, instead of k we can write n there, because we are truncating the series at n. So, we have written alpha divided by beta minus 1 minus 2n is equal to 0. And if you rearrange, what you get? Alpha divided by beta is equal to 2n plus 1. Okay. So, and remember, the alpha and beta are constants which I started in the very beginning. Alpha was 8 pi square me divided by h square, and beta square was 4 pi square mk divided by h square. Okay. If you use these values, alpha divided by beta, and you find out the equation, you put this value here, 8 pi square me by h square and h divided by 2 pi root under mk, what do you get? You get energy is equal to, energy value you have here. So, energy value you get is n plus half h nu, h nu. Okay. So, what does it mean? Alpha divided by beta is equal to 2n plus 1, equation can be written as this one. Okay. So, this is the equation, and this equation you are already familiar. If you have done your vibrational spectroscopy, then their equation you write V plus half is equal to h nu. Okay. Where n could be anything, 0, 1, 2, 3. So, n is 0, 1, 2, 3. This equation you are already aware of. So, what we have found as a solution of the Schrodinger eigenvalue of the simple harmonic oscillator is n plus half h nu or V plus half h nu. It forms the basis of vibrational spectroscopy or IR spectroscopy. Okay. So, this you are already familiar. If you put this value of alpha divided by beta is equal to 2n plus 1 in your equation number 1 from which we started, okay, then what do you get? D square psi by dy square, alpha divided by beta is 2n plus 1 minus y square psi is equal to 0, where n could be 0, 1, 2, 3, because n does not have any limit, because n comes from k value, at which the n comes from k value. The value of k, say n, the numerator of the above equation vanishes. Okay. What does it mean? N could be either 0 or, and what was k? K was the number, integer, because k I introduced here. Okay. So, y raised to the power 1, 2, 0, 1, 2, 3, 4, 5, for that I have written k. Okay. So, k is a number starting from 0, and k I have said k is equal to n when the numerator becomes equal to 0. Okay. So, k is equal to n becomes equal to 0, 1, 2, 3 and so on. Okay. So, the resulting series with finite number of terms is a polynomial called Hermite polynomial, and this Hermite polynomial, now since we have equated the numerator equal to 0, so the number of terms will decrease, number of terms will become less, will not be infinite, sorry, not decrease, will not be infinite. So, a finite series will appear, and this we say as Hermite polynomial, HNY. Okay.